Okay, welcome everyone to this continuation of what is algebraic geometry. We are closing in, and I will almost, this is kind of the last type of topic, kind of differentials and how they appear in algebraic geometry, and then we'll jump to very modern algebraic geometry if you want. Whatever very modern is. We'll see that anyway. But yeah, so today I would like to tell you about differentials, in case you haven't seen differentials before. But in a very algebraic way. So the whole idea is somewhat to reverse history, if you want, or to go back in history. So people were taking differentials and what derivatives of functions for a long time in a more ad hoc, kind of a little bit ill-defined way. So people got a little bit upset with that, and then people invented this epsilon delta calculus to kind of get rid of the ill-definedness of what a differential is. And then eventually people came back to the calculus type approach in contrast to the analysis type approach. And yeah, so essentially I will also just go back to the idea of infinitesimals. And we'll just pull that through and see how far we can go and what we can do with it in algebraic geometry. That's essentially the idea. Okay, so let me just repeat. Hopefully you have seen what a tangent is. A tangent is like the optimal linear approximation on a function, and it really only works in a nice neighborhood, right? In a nice neighborhood it's like the optimal linear approximation, and otherwise it's a pretty bad approximation. A tangent is not a good approximation on a function. It's just a good approximation locally. And the function of the slope of the tangents, that's called the differential or the derivative. And the differential is really more like the algebra behind the derivative. So I probably will mix derivative and differential a few times. But derivative is like the function of the slopes, and differentials is more the algebra behind it. We'll come back to that. But certainly, clearly, I hope you have seen this. It's kind of one of the most important ideas ever. Probably ever. But let's be a little bit more down to earth here. Let's say in mathematics. Okay, very good. And yeah, so semi-classical, they're defined using limits. And what do I mean by that? Well, maybe we'll actually find a good, nice picture. What is a good thing to Google? Probably the derivative of polynomial or something. And then limit or something. We'll see. We'll see what comes out. I, by the way, don't need to spell. Need to learn spelling. It can do it itself. So let's zoom in a little bit. So maybe we'll actually find something that. So this is, yeah, something like this here. Okay, zoom in a little bit more. And you have one time in your life you have seen that. So you have a polynomial and you are supposed to find the derivative using the limit definition of the derivative. And you will do that once because someone forces you to do it, whatever. You're sitting in the calculus class in high school or whatever, analysis in university level or wherever. Someone will force you to do this calculation. So you will eventually do it, but it's somewhat completely useless. You can just learn certain rules how to differentiate polynomials. And for us, kind of we are algebraist. So for us, the universe is polynomials anyway, so it's nothing, the exponential function way to complicate it for an algebraist. So if the universe is polynomials anyway, we essentially don't need the limit definition. We can just go by rules, right? So the limit definition is somewhat useless for us. And this is kind of the idea, because as an algebraist, limits are a little bit strange. I don't really know what that is. Yeah, sure, you can somewhat make that work, but it's not really. And I call that semi-classical because actually the limit definition of the derivative is much younger than the one I'm going to use, which is like the infinitesimal one. So yeah, the infinitesimal one is more like a bag of rules that you can apply, and that's excellent for algebra because algebra is the science of the bag of rules, essentially. Yeah, if you want. So essentially what you should keep in mind here is that we want to mimic a tangent, but we do not like epsilon delta, so we come up with another way of doing it. Okay, so let me just do it for you. Infinitesimals. It's an absolutely great idea, and as I said, literally in your evolution as a mathematician, you start off with infinitesimals. Yeah? You learn rules how to differentiate functions. Then someone tells you about epsilon delta, and they force you to do this limit calculation that we have just seen. Yeah. So let me just pull it up again, something like this, the limit, and then eventually you go back to infinitesimals because that's just more convenient. And here's, for example, the chain rule. Sorry, it's not the chain rule, the product rule. So that's how you would write it with a prime here. And this is how you would do it in infinitesimals. So, well, the infinitesimal of v, the infinitesimal of u. And this is a product. So it's of order 2. And we're doing linear approximation. So we ignore that. So the differential of the product is just the sum of those two. And then you're done. And that's much more like an algebra type argument. And we like that. So the idea, instead of limits, we kind of go really back to the roots of calculus, and we are kind of using differentials as formal symbols, if you want, satisfying certain rules. Now, the different way of making calculus rigorous, instead of epsilon delta, there are many ways, by the way, but instead of epsilon delta, you could just define an algebra satisfying certain rules, and you leave the it's doing the right thing to someone else, and you just go with the back of rules. That's essentially how you learn calculus in high school. They just tell you how to differentiate polynomials. Maybe they actually tell you about, it probably depends on where you learned calculus, whether they actually tell you the limit definition or not. So I think I remember I learned it just as a back of rules, but there was some limit somewhere, but it's too long ago, so I can't really remember. Anyway, so instead of limits, we kind of go back to the kind of classical definition of differentials, if you want. Like the Euler style, if you want. And you realize that you get a lot of things for free just from the product rule. The product rule is like the main player. So for polynomials, the product rule and kind of a starting condition imply the power rule. So the power rule is whatever x to the n prime is n x to the n minus 1. That's the power rule. That actually follows inductively if you know the product rule. So the product rule is good. Product rule, we like that one. Product rule, excellent. Okay, so now we have the power rule. So fine, we have it. And we have the product rule, we like that. And linearity is like a condition every algebra is like anyway. So linearity, we like that as well. And those two together already imply the chain rule. So you can just do it by hand now if you want. I'm not going to do it for you because it's a little bit annoying to just do it on kind of Droid. But anyway, it's not really difficult. So the chain rule actually comes for free from the other ones. Right? And keep in mind that we're doing it for polynomials, which is algebraic geometers. Our whole universe is polynomials, or at most rational functions. Right? Nothing more complicated. And for rational functions, there's another rule. It's called the quotient rule. And it just follows from the others as well. Huh? So you don't really need to do anything. So the only things you really need is a product rule, a kind of a starting condition if you want, and linearity. And you just take that as a definition. As I said, we're making it now rigorous by just ignoring all the difficulties and just take it as a definition. My favorite trick in mathematics altogether, because in mathematics you can just define what you want. Yeah? So you just get rid of all difficulties by just defining it the way it works. Here we go. So for a K algebra, K is our field, and really you should think of polynomials as a polynomial ring, yeah. But principle works for any K algebra. With the omega R, which people usually call the Kähler differentials, the set of Kähler differentials, and it's really just generated by formal symbols, df, the f primes, if you want, differential operators, just formal symbols modulo the formal roots, and exactly the ones that imply all of the others. So the product rule, we love the product rule. Take the product rule. Linear is always good, so we do linear, and then there's some type of starting condition, some type of condition on the scalars. Pretty harmless. And you just take kind of the thing generated by it modulo those roots. Huh? It's kind of really this idea of I tell you how to differentiate, now please differentiate a polynomial. It's really that idea. I'm not going to tell you the limit definition, I just tell you the roots. And that's somewhat enough, right? So that's why we do it. And yeah, right. the localization, in the localization now, the quotient rule is free. That's what we just said, right? It comes for free, we don't need that one. So actually, we can actually define this on regular functions, and then we're in business, because algebraic geometry, right? Polynomials, regular functions, on schemes, on whatever. Huh? And so we'll see that kind of next time. But for today, the idea is just, well, take the rules you've learned that you can actually formally verify in limits, kind of in classical analysis, and just take them as rules. Just that's your definition, and you have no limits anymore, and you can just run it on any K algebra. So you don't need any other conditions. It's kind of, some people, as I said, call it the Kähler differentials, or the R module of differentials, or the operators, or something like that. It goes under different names. It's kind of a straightforward idea. It's kind of nice to just know that all of the other stuff kind of comes for free. And literally, I just pull up this beautiful XKCD comic in a little bit bigger. So essentially, you have everything you need for differentiation there, right? If you remember how you do it, or how you did it, or how you still do it, and it's always just chain rule, power rule, quotient rule, or product rule. Not much more. You don't actually need much more. Nowadays, I would prefer to just run it on a machine, because it is just algebra. It's just an algebra of rules. Just run it on a machine. Kind of the fun in this comic is that the integration is like much more complicated. So what the heck is a Bessel function? There's probably some Gamma function involved if you write down a Bessel function. There's those zoo of functions. So what I would really recommend for integration is, by the way, I think this is very funny, install Mathematica. So if you'd want to do integration, there's still rules that apply, and symbolic integration actually works pretty well. Just do it on a machine. And that got me very far. There was just one time I remember when there was an integral that even the machine couldn't solve, and eventually I found it in an old Russian school book, and they kind of gave you the solution to that integral. That was kind of a very strange situation. So the Russian school book in that case, I think it was from the 1980s, it was kind of better than any type of computer algebra system I could come up with to kind of attack that integral. But that's just a side story. So really, we have all of differential calculus just captured in those few rules. If we care for polynomials and friends and be algebraic geometers, so the only thing we ever care for are polynomials and friends. Anyway, I hope you enjoyed this video, and I also hope to see you next time.